For this test, we're going to be doing some transformations, including translations, reflections, and rotations. For the first question, we have to translate using that vector right there. Now, with a vector, this gives us our x direction, and this gives us our y direction. So this tells us to go 2 spaces in the x direction, in the negative x direction. So we're going to go 2 to the left, and that 8 tells us we're going to go 8 spaces in the y direction, so we're going to go 8 up. If I do that, I go 2 to the left and 1, 2, 3, 4, 5, 6, 7, 8 up. There's our new point right there. We're going to label it Z prime. And we're done for that one. This next one, we're going to have to translate a whole triangle. So what we're going to do is we're going to translate each of these 3 vertices, and then we're just going to connect the dots. We're doing this one according to a rule, and that tells us we're adding 4 to the x, so we're going to go 4 to the right. We're subtracting 3 from the y values, so we're going to go 3 down. So each of these points is going to go 4 to the right. That's 1, 2, 3, 4, and then 3 down. 1, 2, 3 down. And that new point right there will be labeled J prime. We're going to go 1, 2, 3, 4, 1, 2, 3. Will be K prime. And then 1, 2, 3, 4. 1, 2, 3, and that will be L prime. Now that we have our 3 points translated, we are going to connect the dots, and that gives us our translated triangle. On this next one, we have to do a reflection. Here is our line of reflection, x equals -1. I like to draw that, so we're going to draw x equals -1 right there. That is going to give us our basis for our reflection. From here, I just need to count how far we are away from our line of reflection and do that same distance over to the other side. We're going to go perpendicular to our line of reflection. So we're going to go 1, 2, 3, 4 to get to our line of reflection for point A. 1, 2, 3, 4 on the other side, and that gives us our point A prime. We're going to do this for each of these. So D, we're going to go 1, 2, and then 1, 2 back over to the other side. That gives us our point D prime. C will be 1, 2, 3, 4 away, which means it'll be 1, 2, 3, 4 over onto the other side. That gives us C prime. And then B is 1, 2, and that'd be 1, 2 over onto the other side. B prime. And then we're going to connect the dots, A to D, D to C, C to B, and B back to A. And if we do this right, it should be symmetric with a line of symmetry right there across the line of reflection. For the next one, we are going to reflect across the line y equals -x. So that would be this diagonal line right here. And the strategy will be the same as what we had before. We just need to make sure that we are going perpendicular. Now our line has a slope of -1. Perpendicular to that is going to be a slope of +1. So we're going to draw our lines diagonally with a slope of +1. And since we are going with a slope of +1, I'm just going to count from corner to corner instead of from along the grid. So let's start down here with S. We're going to go with a slope of +1, 1, 2, 3 corners, and then over to the other side, 1, 2, 3 corners. We're going to put that on the other side. So there's our point S prime. U is 1 corner away, so we're going to go 1 corner over to the other side, and that would be U prime. And T is a teeny bit trickier. It's 1, 2, and a half to get to the line. So let's go the half, and then we'll go 1, 2 over to the other side. That gives us our point T prime, and then connect the dots, T, U, S, and we have our new triangle right there. So again, we just go perpendicular to our line of reflection and count the distance on one side and match that distance on the other side. For rotations, I like to draw a rectangle from the center of the rotation out to the point that we're going to. So we have this rectangle right here. That gives me kind of a reference that I can use to rotate. And if we're going 90 degrees clockwise, that shape is going to rotate this direction, 90 degrees. Now with our box, I've got this vertical line right here. If I rotate that 90 degrees, it's going to lay down along the x-axis, and it's going to have the same length. And then this edge right here of the box is going to go right along the y-axis, and it's going to have the same length pointed down. So when we draw our box again, we've recreated that, rotating it 90 degrees. F was on the corner of that box, and it's going to be on the corner of this box again, and we've got point F prime. Now when you're doing this, it makes a pretty big mess to draw these boxes over and over again, so I try to draw them lightly and then erase them after I'm done. Let's do E. We're going to draw again our box from the origin out to point E, and we're going to rotate that. So this line will rotate 90 degrees, and it will now be pointed down right here. And the line that was pointed down is going to rotate 90 degrees, and it's now going to be pointed to the left over here. And then we can finish out our box, and we know that point E was on the corner, so point E prime is going to be on the corner right there. Let's color our F prime green so we can have matching colors with this. I'm going to erase my boxes, and we're going to move on to the next one. So let's draw our box on point H. We're going to go out here. That gives us again our two lines. We're going to rotate this one 90 degrees. It's going to put it vertically along the y-axis right there. Then we're going to rotate this one, and it's going to put it horizontal to the left on the x-axis right there. That allows me now to finish out my box. H was on the corner, it's still going to be on the corner here, and now it's labeled as H prime. Alright, let's clean up these boxes. We now have 3 of the 4. G is actually the easiest one to rotate because it's right along the axis right here. So if I rotate that, it's going to be right along the axis right there. And we have our point G prime. Connect these dots, and we have our shape rotated 90 degrees clockwise. For our next set of questions, we have to determine the number of lines of symmetry. The first one is a regular heptagon. It has 1, 2, 3, 4, 5, 6, 7 sides. And our lines of symmetry are going to correspond with those. If I go straight down, for example, that cuts this off. Right there, we have a line of symmetry right down the middle. But since it's a regular heptagon, we have one that crosses from a vertex all the way through the opposite side. Along each of these vertices, they're going to cross over each other in the middle. And we're going to do that for every single one of these. Since each vertex has one of its own, that gives us a total of 7 lines of symmetry. The triangle is going to be the same, except instead of having 7 vertices, it has 3. So we've got those 3 lines of symmetry, 1, 2, 3 right there. And the rectangle is a little different here, so we are going to have to cut this from edge to edge. So we have a line of symmetry there, and a line of symmetry there. And those are our 2 lines of symmetry for this one. It's a little different. It doesn't have 4 like the vertices because it only has, it's not a regular shape. So this one is an unusual number of lines of symmetry because it is an irregular shape. For rotations of symmetry, I like to picture them like we see over here on the edge where this shape is rotating, And rotations of symmetry mean simply that when you rotate it, how far do you have to go until it returns to its original shape. So you can see that this and this, every time I rotate it 90 degrees, it looks exactly the same as it did before. So for a square, we have 90-degree rotational symmetry. So we're going to write that down, 90 degrees. And on this one, sometimes people will say, well, we've got 90 degrees, but then we also have 180 and 270. We don't need to mention any of those because the 90 degrees will build up all of those rotations of symmetry. So it's enough to say the smallest number, which for a square is 90 degrees. For this parallelogram, I've got to rotate this all the way 180 degrees before I can return it back to its original shape. So the parallelogram has 180 degree rotational symmetry. And then another 180 degrees and we're back to its original position. Now this regular hexagon, I like to think of this one as how many different times can I rotate it, because this one's a little tougher to see than the square. But we can see that we have 1, 2, 3, 4, 5, 6 different positions where it's the same shape as it started with in a complete rotation. So thinking about this, I've gone all the way around 360 degrees, and there were 6 different rotations. Again, 1, 2, 3, 4, 5, 6. 6 different rotations in 360 degrees. Each of those rotations is going to end up being 60 degrees. So the regular hexagon has rotational symmetry of 60 degrees, and if we have a regular shape, we can do this calculation for any of those shapes, even the square. If we did 360 divided by 4, because it has 4 sides instead of 6, that gets us 90, which we saw that was our rotational symmetry right here. Thank you guys for listening, and good luck.